Hello, everybody. This is our first thing for today, our What Should You Be Forgetting Today in Science. So, since you and your table partner should be starting this at pretty much the same time, I'm going to ask that you pause the video here and do this the way you normally would. Take a few minutes, maybe 3 or so, and both work on these questions on your own, on your whiteboard. And then when you're both done, take a minute and a half and make sure you introduce yourselves to each other and tell them what you think about New York City, since that's where I am today. Want to go, not want to go? Have you heard good things about it, bad things about it, anything like that? And then go over the answer to these questions now. So pause here, and when you've done all that, unpause to continue. All right. Today I want to teach you why we experience global winds. That's the other kind of wind. I've been speaking for a bit about local wind. You've already learned that deep currents and local winds are similar phenomena with similar causes. So several weeks ago, we learned about currents and deep currents in the ocean, the ones that go down into the ocean. Those are convection currents, of course. Colder water sinks down, and when it gets to a warmer part of the earth, moves back up, density, and so on and so forth. And local wind works the same way, since the land heats up faster than the water during the day. The air above that rises because it gets less dense, and then it moves over, and we get those convection currents to make local wind. We called that local wind. And I had been telling you for a couple days, I think, that there's another reason we get wind on Earth called global wind. Here's a map of them. Global winds are like they sound, they're global, they follow very long paths, and they're predictably in the same place pretty much all the time. So there's certain places that just always experience this certain type of wind, and they're called global winds. And here's a map, and I want you to pause here and just think, what might cause that? Why might we have certain parts of the earth that have wind that follows these very, very certain patterns all the time? Pause now. Think about it, make a prediction. You can jot that prediction down your whiteboard and unpause when you're ready to go. So that's it. That's today. I want to teach you the reason for global winds, those other types of winds that we haven't talked about yet. So just as a reminder, there's two main types or causes of wind. Local wind, these happen because of unequal heating and density, of course. And these are just like deep currents in the water. Global winds happen for different reasons, and they're like other things. So we haven't learned about those yet. But remember, the word local means like in one place. So they're in a fairly small area relative. And global winds, just like the sound, are global, like all across the globe. They're very huge areas. The wind travels very far. There's some maps or some images you might see that show you the global winds, like where they take place and what sort of shape their path takes. And I think as you look at these, they may bring to mind something else. All three of these are global wind models. So sometimes you see it on a map like this, like a flattened out, unfolded Earth, and the patterns look like that. Sometimes you see them on globes or simulated globes like this, and they form in these curved patterns, as you'll notice here. A lot of them have cute names like westerlies and easterlies. The names aren't super important. Scientists like to name things. And they travel in those paths, and they're curved. And you might notice something about those shapes. They may remind you of something else that we looked at before. Very similar. I'm going to take this top map, and the top here, this is a map of global winds like I just showed you. They happen in the air, the atmosphere. And the bottom map shows you surface currents which happen in the ocean. Notice how similar the path of the water and the air are between global winds and surface currents. It's almost like they're the same thing, except one's happening in the air and one's happening in the water. And guess what? I won't yell it because you have headphones on, and I know that's obnoxious. I'm already obnoxious enough. They are. So our big idea for the day, global winds are basically surface currents, but in the air. They're pretty much the same thing, and they happen for pretty much the same reasons. So let me remind you a bit about surface currents. They're complicated, and we haven't talked about them in a while. They're really hard to remember as well. So surface currents are giant circular paths of water that happen in the ocean. They're really big, and they're really slow, if you recall. And they basically follow entire sections of ocean all the way around to the land. I think you had a bowl of water, and we just traced a surface current very slowly around the top of the water. They happen on the surface like that. So surface currents move in curved patterns. And the reason for that is what we call the Coriolis effect, which works like this. Because the Earth is rotating very fast, water, or in today's case, air, that would normally move in a straight path ends up moving in a curved path. So if you think about how the ocean works, we get colder water up here and we get warmer water down here, and we would expect a normal deep current for the warmer water to move to the surface, move toward the colder water, sink down to the bottom, and then move back till it got warmer and move on up. We would expect to see water moving in a pretty straight deep current path up and down the globe. Normally, that would be a natural thing to happen, and it does, except since the Earth is rotating very fast, that straight path ends up being a curved path. And the way that worked, I showed you a couple of videos about why things that are rotating end up resulting in curved paths. I don't have my window in the right place. Let me pause and move it. One thing I showed you was these physicist dudes on this rotating platform tossing the ball. I know you can't hear it. The sound doesn't come through. I don't know if there was any sound on this anyway. And they're on this thing, and then the ball would normally move in a straight path, but since they're on this thing, you end up witnessing the ball moving in a curved path because they're on a rotating object. They're throwing the ball straight toward each other, but it appears to curve, right? The Coriolis effect kind of said things that would normally move in a straight path, if they're on a rotating object, they end up moving in a curved path. Slow motion. That's what caused surface currents and in the water. And then the exact same thing, as we're going to find today, that's also what causes global winds in the air. So same thing, just like the water is somewhat colder here at the poles, the colder parts of the Earth, and warmer here in the middle, we would expect, just like the water, we would expect that the air, when it got warmer, it would rise up, become less dense, and move toward the colder. And then when it gets colder, sinks down lower, closer to the Earth, and would move in a normal, predictable pattern like that, all over the place. And it does. But since it's on a rotating object, the Earth, which actually rotates very, 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 very fast, it rotates about 1,000 miles an hour, I think, something close to that number. Those normally straight paths on those convection currents turn into curved paths on a rotating object. Those curves can become intense enough. There's a lot of curving air in the Atlantic Ocean, which is where we get a lot of hurricanes, and that's one of the reasons hurricanes form. The air gets swirling and swirling and swirling due to that Coriolis effect, and it's there. So that's how global winds work. Same as the surface currents, they just happen in the air. You'll notice they can cross the land because they don't run into the land, so to speak. The surface currents always moved in circles like between the continents because they didn't run into the land, but the air doesn't have anything to run into, so they move like that. You might be thinking to yourself, so these places that you see these arrows basically have wind almost all of the time because of that normal pattern, and they do. You'll notice where we are, we're not really quite in the path of any of the global winds, and that's why we don't experience wind every single day. We're not in an especially windy place, so we don't get it. So that's how global winds work. So just to summarize, if you think about convection currents in the ocean, those manifest as deep currents. The water goes down into the ocean and makes those deep currents. In the atmosphere, convection currents, as we learned the other day, make local winds. They make those winds where you usually see water and air. And in the daytime, not water and air, water and land. In the daytime, the land heats up faster, so you get winds going like this. And then at night, the land cools down faster, so the water's warmer, and you get winds going like this. Changes the direction of the wind. Those make local winds. The Coriolis effect in the ocean, that creates surface currents. And in the atmosphere, it creates global wind. And they pretty much work the same way. So they're really easy things to keep track of because they kind of have a sibling in the air and the water, and the same thing causes both things. If you would, please pause here and write this down in your notebook for the day. This is a biggie. And unpause. I'm going to have you do the big idea too if you didn't, but I'll put that back on the screen. So pause here, write this down. And also, if you didn't write it, I'll zoom back in time here. I didn't have you write the big idea down. Sorry, that's to write as well. Here it is. Go ahead and pause here once more and write down. All right, before we wrap this up, one last thing to think about is models. You usually see these in visuals a lot of the time. Rather than having to memorize what causes these things to happen, you often get models to see. And, I showed you some models like these, with the maps and the globes and stuff. And something to really get you used to, some people make super fancy double models where they show you the global winds on the same map where they also show the local winds, which is kind of cool. So they show the convection currents here, land, water, or warmer, colder. And so you see the local winds kind of off to the side like this. And then they show the global winds in the middle of the map. I think those are really confusing if nobody tells you how to understand them, but they're pretty cool. Here's another one, even fancier looking to me. They show the local winds on the side here, just like this one showed the local winds on the side there. And then they show the global winds in the middle, here and here. These are computer generated ones. They're pretty nice. Sometimes you see people even just draw them as well. If you imagine trying to draw these yourself, they kind of separate the Earth into the latitude sections where these happen, and they draw the local winds off to the sides, the convection currents, and the global winds, Coriolis effect, in the middle. Those are super nice. I find those to be a bit confusing. So a lot of times, like you saw me do, I'll do sort of like a not spinning Earth one, where I show the convection current moving straight, and then kind of show, but since it's spinning, on a spinning Earth, and I'm going fast, I'm almost out of time, on a spinning Earth, those paths become curved rather than straight. And I'll do something like that to kind of show how they work. Communicating and modeling and drawing, important for people to help them understand. Okay, so that's global wind and it's local wind. I'm going to ask you to write down your thoughts on one last question at the bottom of the page you took your notes on today to talk about tomorrow. Here's your you do alone, but you're going to keep it because I want to talk about it tomorrow. It's a pretty complicated question. And I want to have you talk before you turn in. What if the Earth didn't rotate? Or if it rotated really slow like the moon or Mars or Venus? The moon takes like a month to rotate. Mars takes like 2 months to rotate. Venus takes almost a year to rotate. They rotate really, 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 really slow. So what if the Earth didn't rotate it, or if it rotated really slow? How would global winds change? How would local winds change? Both of those, I think, would change substantially if the Earth didn't rotate or if it rotated slow. So I want you to jot your thoughts on that question down. This is an advanced you do alone, really an elaborating thing. After you've got that done, you're done with this part of the lesson and you're ready to move ahead on eClass. Hope you learned something today, and on to the next thing.